possible to introduce Dr. Rebecca Randall. She's talked with us before and it's always been really, thought-provoking and really interesting. So I'm sure, no pressure, it'll be just as good. You can't go wrong with things like elements of like and so world history anyway. So without further ado, we're going to have the talk first, then we'll stop for refreshment and then we'll do questions after that. Okay.
Yeah, thanks everyone. This is my third time here, so thanks for coming. Hopefully this isn't too loud. I've talked in the past about my own research. Right now I'm working for Trelleborg, and they're a polyurethane manufacturer in like North Nottinghamshire. And some of the work we do is now like commercially sensitive, so I can't talk about my work anymore. So I thought I'm going to talk about something more sort of general, and something that was the sort of thing that got me into chemistry in the first place. My background's in chemistry. I've been working at it for almost 10 years, over 10 years now. So I'm going to take you back to, I think I read this book in maybe my GCSEs at high school. This book here, and also this book. So some of the things I'm going to talk about in this presentation are shamefully stolen from this book, and I would encourage everyone to read them. Popular science is, and this is, my own opinion as a chemist, dominated by space, and physics is the most popular science. People love to read about space and planets and science fiction, but chemistry books are a lot harder to find. So when we find them, we tell everyone about them. And if you are more of a sort of true crime fan, I would also recommend these two books as well. These are about the history of poison and how different elements impact the human body, with some real sort of history cases in there as well. I remember reading this on holiday. My mum was worried that I was going to poison the family. So yeah, but recommend all four of those books. So what I was going to do is I'm going to pick sort of three elements, for want of a better word, about chemistry, at points where it's been influenced by society, or maybe it itself has influenced an event in history. This is the sort of things that drew me into the subject, because it's seeing the real world impact of the science. So hopefully you feel the same way. So first up, I'm going to talk about a time when chemistry got a little bit political. So this is the periodic table. You might be familiar. You probably know carbon, oxygen, hydrogen. These are ones that people tend to remember the names of. But there's some really obscure ones, particularly in this sort of heavy elements at the bottom, with really strange names like europium, americanium, californium. In fact, lots of different elements in the periodic table are named after locations, or countries, or specific places in a country. Sometimes this is like just where they were discovered, and in the sort of natural earth elements of the periodic table, some of them are naturally occurring. They were named after where they were discovered. But particularly down this end, when they start to be synthesized and manufactured by researchers, then becomes kind of fair game. If you discover or make that element, you get to name it. So this is where you start to get a little bit of the political element coming in. If you can get to it first, you can name it, and you can name it after your workplace, your country, your favorite scientist, a colleague. It does start to get quite contentious. There's also quite a lot of elements in the table named after people. So people probably know Einstein. So we've got Einsteinium, number 99, and we've also got curium as well. But there's quite a few others that are all named after other scientists. There's Copernicus has got one, Rutherford has got one, and Mendeleev, who was the person who came up with the idea of the periodic table in the first place. And the story I'm going to tell includes Mendeleevium. There's two who also come into the story. These two elements here, they are the only two elements in the periodic table to be named after someone whilst they were still alive, which is, I think, meant to be one of the biggest honours in science. You get to be immortalised in the table and know about it. So it's pretty impressive stuff. So Another way that naming can be a little bit political, which also leads into the story, is certain people, even though they weren't born in that country, became big names at the university they were working with. For example, Einstein spent so much of his time at Princeton, he started to become almost synonymous with it in certain circles. So when they name an element after Einstein, you get a little bit of a boost for that university. And in an academic world where funding is everything, even like a little slight, note to someone this big, it means a lot. And same with Rutherford for Cambridge. He was a big tie there. Including Einstein, there are 4 people total who have elements named after them who were involved in the Manhattan Project, which I thought was quite an interesting fact. And the person I'm going to talk about a little bit more is Glenn Seaborg. He's one of the people who has an element named after him whilst he was still alive. That's him pointing to it just there. So, Glenn Seaborg, he's a pretty impressive guy. He's a Nobel Prize winner. He's been an advisor to many, many presidents on atomic energy and the nuclear arms race. And he's a team leader at the Manhattan Project and a leader at Berkeley, California. This story is about how he worked to discover or co-discover 10 elements over the course of quite a few years, obviously. He was quite an interesting guy. He announced some of these elemental discoveries on a children's radio show called Quiz Kids rather than an academic journal. And it was a massive boost for the university at the time. Berkeleyum is named after Berkeley, the university, and California after California, where the state was. So that's 2 big hits for the university right away. Now, this was all sort of happening in the 1960s. So around the same time as the space race. And this becomes important because it was quite controversial at the time when they discovered mendelevium. It was quite a big thing at the time to name an element after a Russian scientist during this sort of Cold War animosity. The way they've made these elements, so if you think back to the periodic table, those big, like the long sort of section at the bottom that's almost been taken out, called heavy elements. These are the ones we're talking about here. They've been synthetically made, usually by getting something that already exists that is quite heavy, and then you just pelt it with alpha particles. So you basically just keep going until it takes on something, gets slightly bigger, and takes on more mass, takes on more neutrons, electrons, and it's usually incredibly unstable. And then maybe a millisecond later, decomposes and it's gone. But if you can detect it during that millisecond, it exists, you've made it and you can name it. So that's the sort of thing that they were doing in the 60s. I think, in fact, one of the elements, I'm not sure which, Seaborg connected up the fire alarm in his chemistry building to the detector. So when they discovered the element, the whole fire alarm went off for the building. So it's a big moment. And this was all going really well for them until in Russia, another group started using exactly the same methods to sort of get to the same point of them and then to push it further. They wanted to now look in, instead of just bashing things with alpha particles to try and force it to get bigger, they want to fuse 2 smaller elements together. So they started doing a form of, sort of cold fusion to make bigger and bigger elements. And they come out in 1964 with element 104 and then 105, which they name after their own university, Dublium. Then, as a result of this, the team at Berkeley don't take it very well. They say it's all falsified. They don't know what they're doing. It's all errors. They massively dispute the journals and the articles. And then they try to recreate these methods. They try to make 104, 105 themselves and don't quite make it until 1974, when both teams make element 106 months apart from each other. This is where it all sort of bubbles over. Both of them have different names, same element. The journals in both countries refuse to call the element the other team's name. And throughout the world, there's a lot of side taking, and to the point where the international standards of units and scientific measurement, IUPAC, have to step in and make a sort of judgment call. And in the end, they did actually want to take seaborgium out as an element, but the Berkeley team kicked back so much that they sort of rescinded on that, and he managed to keep his element there. So after this point, there is a sort of limit to the periodic table. This was a real point in that era of the sort of space race of the 60s where probably the environment around them was just channeling this competition and this need to like just make more and more and more elements. It was a bit of a national pride at the time to have made the newest element. And then after this point, Germany sort of came in and the playing field diluted a little bit and this animosity went away. And it has a semi-happy ending. Obviously, the situation with Russia isn't amazing at the moment, but in 2002, there was a joint institute for nuclear research in Russia, where a team of both Russian and American scientists synthesized this element, 118, ognesium, which is named after Yuri Ognesian, who is there. And he was someone who developed cold fusion as a method of creating these heavy elements. So there's an element on both sides. Both parties have got someone who gets to claim some things. So it ends well, but there's still obviously a lot of other instances throughout science where this rivalry and country rivalry comes into the work. So that's the story about political elements. And now I'm going to talk a little bit about where chemistry has been influential or has weaved its way into art, into our culture. There's a few examples of this. They're all a little bit short, so I've packaged them together. So this was just to make a point. So science has always managed to influence our culture. Just by being a popular thing that's discovered, people think about it more. It tends to find its way into art, into books, into literature. And this is an example. So this is a short story written by Mark Twain 6 years after the discovery of radium. And radium was incredibly popular. It was in loads and loads of products, glow-in-the-dark clocks. It was in skin cream and whatnot before they realized it was incredibly harmful. And in this story, it's about someone who sells their soul to the devil. When the devil appears, he describes them as being green, glowing, made of radium, he even calls it out, with a skin made of polonium. So almost a little science fiction writing from Mark Twain, which is quite interesting to see. And similar to this, there's a phenomenon that I cannot remember the name of, but it's known that when a new material is discovered or at least popularized, there's a big rise, like a notable rise in the number of sort of mental health cases of people who believe they are made of that material. So an example is, I think George III, when glass became a lot more popular and accessible, had a period where he thought himself was made of glass, and it's been noted for other materials that come in, like new metals and whatnot. So it does come into the psyche at any scientific discovery, which is quite interesting. Another little quick one is about mercury. So mercury, you probably know, you've seen it in a thermometer perhaps. It's sort of liquid ball bearings and they all flow together. It's an element in itself. And there's a reference to mercury, which is also known as quicksilver, even in Shakespeare. There's a line in Hamlet about poison being as swift as quicksilver. So even in Shakespeare, it's there. Now, mercury itself as an element isn't too harmful, but when you get a form of it called methyl mercury, that's when it becomes incredibly toxic. So this is the reason we don't use mercury in thermometers anymore. So the reason that it is toxic is methyl mercury can pass through your blood-brain barrier and it reacts there with some enzymes irreversibly and then can't get back out again. So the more you're exposed to it, the more it builds up slowly and slowly over time. And what it does is it essentially stops antioxidants playing a role. So, and in your brain, you have a lot of oxygen, so you're particularly susceptible to oxidative damage. So without these enzymes, you have basically oxygens with extra charge that are called reactive oxygen species. They're just damaging the sort of neural networks. And over time, with exposure to mercury, these fry away, and you get symptoms that are quite similar to advanced Alzheimer's. And there has been this long sort of cultural knowledge, even subconsciously, about mercury exposure and madness. And the example is that hatters used to use bright orange mercury to separate fur from their pelts. And they had this reputation for losing their hair, for going a little bit mad. And there's one example that springs to mind is the Mad Hatter in Alice in Wonderland. So in a way, you can still link chemistry to that character as well, based on this sort of built up knowledge over the years. The last little story from this section is about poison and colour. So these are two very, very different men, Napoleon and Van Gogh, So both were thought, or there's theories that they were killed by their love of colour. So Napoleon, as I'm sure you know, was banished to an island after he lost the Battle of Waterloo, and he loved the colour green. Apparently the whole house was full of green wallpaper, green everything. And the colouring that they used to make green wallpaper at that time was arsenic containing. And it's known that arsenic tended to come out of the wallpaper in humid conditions. And Napoleon was known for taking very long baths, and it was very humid in the island, especially the summer he died. So there was this theory for a while that perhaps he had been poisoned by arsenic, and he died of cancer, I believe, but it could only have worsened his state of health. And I believe they actually tested his hair recently after death, and there was an incredibly high amount of arsenic in his hair. So there's proof there that chemistry played a part there in his death. Similarly, but a little bit sadder, Van Gogh, he was using paints that at the time lead was commonly used in both white and yellow paints, and obviously he used a lot of yellow in a lot of his work. And it was known and noted that he used to sort of lick his paintbrushes quite regularly. So there's a school of thought that he was ingesting lead that way. A lot of the symptoms that come with lead poisoning are quite similar to what Van Gogh was experiencing. The sort of amnesia, seizures, and abdominal pain. And as his condition worsened, it was noted that he started to eat his paint, either through a seizure or through an attempt at self-harm. And, you know, it probably got a lot worse for discontinued lead poisoning. But one, I guess, for want of a better word, sort of silver line to this is quite interesting. Apparently, when you get quite advanced lead poisoning, one of the symptoms that comes up is that when you look into the light, you see sort of auras around it, sort of circular spiraling auras around light sources. So there's a theory that his advanced lead poisoning led him to see the stars and the moon in a slightly different way, something with an aura around them. And that's what he was trying to paint in things like Starry Night. It was genuinely how he saw the world as a result of lead poisoning. So if true, that is very interesting. So as I said, 3 stories. This is the last one. This is right at the back of the Disappearing Spoon book, and for whatever reason, it's the one that stuck with me the most. I think it's dead interesting. So this is about tin and the way it's potentially sabotaged quite a famous expedition. So to understand this, we need to understand a little bit about structure and why structure is so important in chemistry. So for that, I'm going to use a quick example of something that is a phenomenon in chemistry called chirality. So chirality essentially is non-superimposable mirror images. So in the way that your right hand and your left hand are mirror images of each other, but you can't put them on top, you can't move your hand around to be the same. It's that essentially. So you can have 2 molecules that look very, very similar, but you won't build a bond will be one way and one bond will be the other, and they'll be completely different to each other in the way that they interact in certain areas. And the human body is a big one because the human body itself is chiral. DNA spirals a certain way rather than the other way. So chiral molecules can interact with chiral DNA in different ways. One example actually is that peppermint and spearmint, I believe, are chiral molecules of the, they're the same molecule but slightly turned a different way. So they taste different, for example, even though they're chemically identical, which is dead interesting. A sadder example that's probably more well known is the thalidomide drug, which was sold as a morning sickness drug. And one chiral isomer was very, very effective at being a morning sickness drug, while the other one unfortunately caused quite significant birth defects. So there was a huge generation of children. I think it was even on an episode of Call the Midwife recently. It's been brought back up again. Who suffered, I think they were born without limbs, and there was a huge payout as a result for the drug company. And this was purely because when they sort of scaled up their lab tests to a big pharmaceutical production, they were giving this drug, but they were giving a mixture of both of them. So it was effective for its purpose, but it was also had this sort of secret, slightly different, but chemically the same. It would have been a completely pure drug, but just because this bond's going that way, it interacts differently and had horrible implications for the children. So thinking about why structure is so important in chemistry, another example of this is something called allotropes. And this is meaning that something is made up of exactly the same atoms, but it's just arranged differently. So carbon is a good example. So carbon can connect to 4 other carbons. It has 4 bonds. And carbon and graphene at the end of your pencil are exactly the same. They're just made up of carbon and nothing else. But under high pressure, these carbon atoms arrange this nice diamond structure, which gives it all the properties of diamond. It's shiny and beautiful and hard and really strong. In graphite, when it doesn't have that additional pressure, it creates sort of just sheets where the carbon atoms are only bonded to sort of 2 others rather than 4 others like this, or 3 others, 4 in total. And you don't get bonds between the layers in the way that you do in diamond. And that's how pencils work, essentially. You put it across the paper, this bottom layer comes off onto the paper, leaving a mark, and so on and so on. So it's very, very fractious, but exactly the same chemically as diamond. There's something else that does this exact same thing is tin. So tin changes from this structure to this structure at 13 degrees. And the main thing to note here, like you don't need to take in anything about this diagram other than this is bigger than this. So when it cools down, it expands into this like larger structure. And in chemistry, atoms tend to like an area that is larger. So when you boil water and create steam, that's a favorable reaction because it's going off into the air, it's got energy and it's got space to move. So in general, things that go to this like larger space are favorable and more likely to happen. So when it expands, it causes fracturing. And because it's an elemental shift in structure, it sort of starts at the surface and then it eats its way through. I think it was called like tin plague or something colloquially. It almost eats through the whole material quite dramatically. I've got a speeded up version at -40. You can see like the extent of the damage. I think this was about over an hour. And when it breaks apart, it apparently gives out a sound called tin scream. You can hear it ripping apart, apparently. I've not heard it, but so it's quite significant. So there's a few examples where this has been noted through history. Something as small as when coins used to be made of tin, people used to notice like what they thought was sort of white rust forming on it, which was just a form of this alpha beta shift. And obviously it eventually turns your coins to complete dust, so they stopped using tin. Another example is in St. Petersburg. There's a lot of examples of colloquially of church pipes, organ pipes just exploding. At the time it was blamed on the devil, but it could be that they were just made out of tin and it was a cold winter, a vibration went through it and the whole thing cracked. Another example is Napoleonic Wars in Russia in the 1800s. the buttons on the coats used to have tin components to them. So there are reports that all the tins or the fastening or the buttons of the coats just crumbling, breaking apart. So the soldiers didn't have as much protection from the elements. They didn't have the same sort of strength and morale, perhaps, as the other army. So in a small way, maybe chemistry influenced that as well. But the biggest one that people might be sort of more familiar with is Scott of the Antarctic. So this is the example in the book, which I thought was quite it's quite sad but quite interesting. So the plan for Scott's expedition, and a lot of things went wrong. Like I think he missed a dog sled, he missed something out. The weather was bad. There was lots and lots of factors. This is just one of them. But the plan it was to start somewhere, and they go obviously to the pole and back. Along the way, they bury these containers in the snow. And the idea is they put their fuel and their food for the way back in these containers. And then when they get there, they turn around, they dig them up on the way back, so they don't have to carry as much, and they can dig it up on the way home. They've got enough. However, not the tins themselves, but the solder that kept the tins together was made out of an incredibly pure tin. And when they were put in the snow, and this process of cracking is catalyzed by dents as well, and you can imagine a canister on an Arctic expedition would probably be dented. They all cracked, and it was noted in the diaries that they came and they dug up the provisions and they were all broken, all the fuel went into the food and nothing was usable. So they lost like a great amount of their provisions for the way home, possibly due to a chemical shift in the solder of the canisters they took with them. And as I'm sure people know, only 12 miles from the next depot, the whole expedition crew passed away. So that's quite a sad one to end on. So I put a nice little happy thing at the end about beer. Yay. And so this is something that my old flatmate always used to say about people pouring Prosecco, that it was all surface chemistry, and she's right. So this is just a little bit about surface chemistry in a glass of bubbly, just to end with. An example of chemistry in the real world that everyone's probably familiar with. So as I'm sure you know, if you pour something straight in, you get a huge head. And if you angle like this, you get less of a head. And there is no right answer about which is the better one. It's kind of up to you. It's kind of personal preference. But I'll tell you what the difference is. So if the bubbles, the CO2 in something like Prosecco, gives it texture, it gives it a sort of tangy flavour because CO2 is acidic. And when you pour something like this and you reduce the loss of CO2, you keep some of that flavour. But if you are to pour it straight in and you get a big waft of it, you increase like the aroma of the drink. So you get that adding to the experience as well. So there's maybe a bit of a middle ground there. And if you want aroma while you're drinking it, maybe you want a little bit ahead, but you don't want it all to go in one go. But also if you have a big head at the start, it's probably better for your digestive system after you drink it because all the bubbles are gone. There's a lot of factors basically. And something else, if you're really into this sort of surface chemistry, if you have glasses that are old, that are scratched, even like small imperfections in the glass, these are where bubbles form. That's the reason bubbles form, is they cling onto these little imperfections, and that's where they come from. So if you have an old glass, you'll probably notice that all your drinks are a lot fizzier, basically, because there's more little cracks for the bubbles to form on. And the last little bit from me is about Guinness. So this is a question, actually. I don't know does anyone know why or what effect nitrogen has on Guinness? Like, why don't they use CO2 in Guinness? Why do they use nitrogen? So the reason they do, so it goes on, yeah. So the reason is basically nitrogen is less polar than CO2. So the oxygen atoms in CO2 just really like electrons. They draw electrons to them. They're negatively charged, even in a bond. So you get a more negative charge on ends of the molecule, and in the middle it's more positive. Whereas nitrogen, it's two of the same thing, so it's just a bit less polar. And that has an impact on the way it bubbles. Basically, it makes the bubbles are unable to expand as much because of that lack of polarity. And that means you get tighter bubbles. It means that your brewing can withstand more pressure. And it also has an impact on the way the head forms. So in a normal like, pint of lager, you'll get a head that dissipates quite quickly. In a Guinness, you get this sort of tight textured foam because the bubbles are smaller. And that obviously adds like a creaminess, it adds a texture. And if you sip a Guinness, people usually shout at you because you're just getting a mouthful of nitrogen. You need to do a big gulp to get the full experience. I've been to the Guinness factory recently, so that's why I'm saying that. So it's all about polarity of the bubbles, which is quite interesting. So I'll leave you with that. I hope you enjoy Guinness in the near future. Maybe it's not the weather for it right now. And just again, I'm going to put the books up. I think they're great books. Please read them. Some of the stories are from these two. Some of the poisoning ones are from these two. Even if you just dip and dive in, these two are quite heavy in terms of the science about how poison affects the body. But these are very, very easy reads. As I said, I read them in high school, and they're just very short chapters to pick up and flick through. I reread a few chapters of it in making this presentation, so it really is an easy read. Hopefully you've enjoyed some of the stories, seeing the ways that chemistry has influenced history or art around us and played a part in the lives of some very famous people. And I've made a little case for why chemical popular science books should be considered up there amongst space. So thanks for your time. I know we're going to have a little break, but I'm happy to answer questions afterwards.